In this section, we're going to look at differentials. And essentially, the idea for differentials we've seen in a way before when we defined what the derivative was. We defined it in terms of basically rise over run, and then we put a limit out front to make it exact. So we're kind of going to return to that a little bit. So the function that I'm going to work with for this example is just x cubed. Pretty easy. And I'm interested in what is happening near x equals 2. And then I need another thing which I'll explain in a moment what this is. Sorry, this should be 0.1. Okay, so don't worry about what this means right this instant. Okay, so if I plug in 2 to this function, I get 8, and that's no surprise. But the question I want to ask is, what happens if I plug in numbers which are close to 2, but not actually equal to it? So the idea here is, so let me plug in here f of 2.1. And why 2.1? Well, I'm thinking of this as being f of x plus delta x, which delta x is this thing over here. And what I get if I compute that is, so what we need to just compute there is what is 2.1 cubed. And we can just do that real quick with a calculator. And we get 9.261. Okay, and that's not a big deal. And then we had already said that f of 2, this one we can compute exactly, is just 2 cubed, and that's 8. Okay, so f of 2.1 minus f of 2 is 9.261 minus 8, and that's, of course, just 1.261. Okay, and so this difference here is what we're going to call delta y. And basically what that is it's just literally the difference between the two, right? So in the rise over run kind of schema, this is the rise, what we ended up at minus where we started, and we got 1.261. Okay, so that's fine. Now the other thing that we're going to ask though is how can we approximate this using a little bit of calculus? Okay, and so this stuff is what we'll call a differential. So the differential that we're going to have is what we call dy. Now dy and delta y are somehow different, and dy is defined to be this quantity. You may ask why that's true. In a way, basically what we're doing is, remember how when we started talking about derivatives we said there were two different notations for it. The left-hand side here is Leibniz style notation and the right is Newton style. Well, if we pretended that dy dx is a fraction, we multiplied both sides by dx, then we get this. Okay, so dy is f prime of x dx. Now for us, for this particular set of values, dy is f prime of 2 times dx, and f prime of 2, well, I don't know what that is yet, so let me come down over here and let's just figure out what f prime of x is. We get 3x squared, and so f prime of 2 is 2 squared is 4 times 3 is 12, and so I get a 12 here. And then dx in this particular case is 0.1, so 0.1 is here. And so if I multiply these, I get 1.2. Okay, so now let's look at the answers that we got. We got 1.2 here and 1.261 there. And they're close to each other. They're not going to be exactly the same, but they're very close. Now, what do the two things mean? This is literally what is f of 2.1 minus f of 2. And this number we got by doing a little bit of calculus. Because basically this is the slope of a tangent line. That's what the derivative is. And then, yeah, so basically if we've got a curve here, so let me just draw something, then the difference between the two things is delta y gives me literally the rise of that blue line. And this other thing is giving me, I'm computing this basically, what's the slope of the tangent line, and then what does the tangent line do over this distance. And now you see, of course, this graph is perhaps not the best, that the two things aren't the same, but for small values of delta x, or dx, these two things are going to be relatively close to each other. So what that means is that if we're interested in a function and we want to do numerical computations, so like in this case, what is f of 2.1, we can approximate it without having to actually crunch this with a calculator. And because notice that this multiplication here was very simple to carry out, whereas doing 2.1 cubed was kind of annoying computationally. Okay, so this is all pretty easy right now. We'll look at the more exotic stuff in class. But basically, just for now, think of delta y is the actual difference that you actually compute, and dy is something that we get with calculus that approximates it.